Okay, so today we're working on Objective 3.4a. The topic today is inverse functions. We'll be using algebra to find inverse functions, and then we'll use algebra to check our work to make sure that we did it correctly. So our essential questions are, how do I know a function is one-to-one? Critical that it's one-to-one, and if we're going to find its inverse. Number two, how do I find inverse functions algebraically? And then how do I check my inverse work algebraically? So if you recall, a one-to-one function is a function. So we know it's a function because it's called a one-to-one function, which means it passes the vertical line test, which says that every x has exactly one y. Well, a one-to-one function is a function where each x has one y and each y has one x. A test on a graph would pass the horizontal line test. Okay, so those are things to remember. Remember that the horizontal line test doesn't mean if I graph the function and I draw a horizontal line anywhere along the function from bottom to top, I'll only touch the function in one spot because each y has one x and each x has one y. And there's a theorem that goes along with a one-to-one function that says increasing or decreasing functions are one-to-one throughout their domains. So for example, if I have let's draw a quick graph here. Here's the xy axis. And if I have a graph that's doing something like this as it goes across the domain, you can see that that graph is increasing as it moves to the right. That's increasing at all times. And so if I were to take a horizontal line and I were to cruise across that graph, wherever I go, I will only intersect the increasing function in one place. And it definitely is a function because it also passes the vertical line test. So you can see that that theorem holds true for increasing functions. Let's take a look at a decreasing function. And maybe we'll do one that's just a little more complex. Let's do a rational function. And in fact, let me make these asymptotes. So I'm just going to make these asymptotes and not really call that an x or y axis. All right, so if I were to draw a graph that was doing, say, something like this, and this would be a rational function, and then coming over here and doing something like that, you can see as we're going from left to right that on this side that curve is decreasing, and then once we jump over to this side, it's also decreasing. And so if we were to take another horizontal line and drag it across our function, you would see that it is definitely one-to-one because it passes the horizontal line test. And so the theorem also holds true for decreasing functions, that they have to be one-to-one, versus if I had something like for a quadratic, for example, a parabola, this would not be a one-to-one function because over some amount of time it's decreasing, and then it turns and it increases, and you can see because it does change direction that it fails the horizontal line test, and therefore a parabola, a quadratic, or a fourth degree polynomial or sixth degree, those would not be one-to-one functions throughout their domains. Okay, so let's first just talk about how we know a function is one-to-one. So let's take a look at the first one. We have f of x equals 3x plus 7. So that's a linear function, right? Has a positive slope, so the slope will be increasing. And if we were to just graph it quickly, we could see, so here's our x-axis here, here's our y-axis here, and let's see, we'll just go by 3. So that's 3, 6, 9, 12, whatever, it doesn't matter. I guess I could have gone by 5s. Doesn't matter. So our y-intercept here is 7, and our slope is rise 3 and run 1. And so this is the line here. And so this graph is increasing as it moves across the domain from left to right. Therefore, yes, it is 1 to 1. Ignore the dog, please. Somebody is walking past the front of my house. All right, let's look at this next one. All right, this next one is quadratic. This is a parabola, right? So if I were to graph that, you can see that that's just the parent function, y equals x squared, shifted down to -9. So if this is -9 here, then your parabola is going to do something like that, right? And so that is definitely not 1 to 1 because it decreases on the left and then hits the vertex and then increases on the right. So how can you constrain a parabola so that it is 1 to 1? Basically what you're doing is you are constraining the domain to either the decreasing interval only or the increasing interval. So like for example, I could constrain this to be 1 to 1 if I said x was greater than or equal to 0, because then that would cut off this whole side of the graph so that we were only looking at the section of the parabola that was increasing as you moved across the domain. Or vice versa, we could decide to go x is less than or equal to 0 and pick the left side of the domain, which would be fine as well. All right, let's take a look at this last one here. We have a cubic function here. And so cubic functions, this is a pretty basic cubic function. It's not too difficult to graph. If we were to graph f of x equals x cubed, that just means we'd go 0 is 0 cubed is 0, and 1 cubed is 1, and -1 cubed is -1, and then 2 cubed is 8, and -2 cubed is -8, and so it would do something like that. That would be the parent function. So if we look at this graph, what's happened is the parent function has a vertical flip, so it's flipped upside down, and then it's shifted up 2. So this the 0, 0, 0 would move up 2, and then the points would just flip, and so this graph would look something like this. So it would do something like that. And so you can see because of that negative flip on it, it is decreasing as you move across the domain. And so we would say that yes, this is 1 to 1. Now algebraically, there's other ways that you can prove that they're 1 to 1 by solving it for x. And so or switching the x and y and then solving it for y, and you'd only have one y. You wouldn't have a y squared or y to the 4th or something like that. So let's go about how you would do this algebraically to determine that. Okay, so in order for a function to have an inverse function, it must be 1 to 1. It has to be a 1 to 1 function, 1 x for every y and 1 y for every x, and a couple little important things to remember. So important details. Okay. Inverse means, so let's talk about inverse operations. So you have inverse operations, right? So what's the inverse of adding? The inverse of adding is subtracting, right? The inverse of multiplication is division. So those are inverses of each other. The inverse of taking something and squaring it would be taking its square root, right? Same thing, whether you're taking something cubed, then you would take its cubed root, etc. X to the n, that would be the nth root. And so these are just your inverse operations. And so when you're finding inverse functions, you're using the inverse operations to find them. So that's important to note. And now let's go and fill out our guidelines for finding. This is, by the way, this right here. This notation does not say f to the -1. This says the inverse of the function f, or f inverse of x. Okay, so either of those are critical, but this does not mean, it does not mean 1 over f of x. Okay, this is not a negative 1 exponent. It's an inverse notation when we're talking about function notation. So here are the guidelines for finding the f inverse of x, or the inverse of the f function in simple cases. So we're going to replace f of x with y, just so that we can use some algebra here, x's and y's. Okay, we're going to switch the x and the y. That's critical. That's what inverse functions do. The x coordinate and the y coordinate switch places. We're going to solve for y, and then we're going to replace y with f inverse of x. Okay, and so things to remember, that if you have a set of points here, and this is point A, B on the original function, then on the inverse function, those 2 points would switch, because what happens is x's and y's switch when we're doing inverse functions. Okay, something else to note is that the domains will also switch. So the domain of this function, for example, let's just do an example here. So let's say the original function has a domain of 0 to infinity and a range of 2 to infinity. Then the inverse function, because the x's and y's switch, the domains and ranges also switch. So the domain of the inverse function would be the range of the original function, and then the range of the inverse function would be the domain of the original function. So those are just critical little pieces of information that will be very helpful when you're verifying things, and it'll be really helpful tomorrow when we use graphing to find inverse functions. Okay, so after we find the new inverse, step 4, we're going to verify the 2 functions are inverses using one of the 2 methods, and today we're going to be using the algebraic method. And so algebraically we will be using the theorem of inverse functions, and I will talk to you about that in just a moment. Graphically, we would do a test to see if the function and the inverse function are symmetric with respect to the line y equals x. And we will talk about that tomorrow. So today we're going to use algebra and the theorem of inverse functions, which I'll show you in just a moment. Okay, so we're going to go first and find some inverses algebraically, and then I'll talk about the inverse theorem, and then we'll do some checks and we'll be done. Okay, so we're going to start with our function here. F of x equals 2x plus 5. So that's a linear function, so we know it's 1 to 1, right? It's got a positive slope, and it passes through it passes through the y-intercept is 5, and then it has a slope rise 2, run 1. So we know it's increasing all the time. I'm not really going to graph it there. So what we do first is we switch f of x with its alternate notation, which is y, because remember, f of x just really means y. Okay, so we're going to do some algebra now. So to do inverse functions, what we have to do first is switch the x and the y. So I'm going to do that. So x equals 2y plus 5. So there's just a switch there, so I guess I'll color code that. All right. So then we'll switch the x and the y. So that'll be step 2, and I think I'll go back and write this as step 1, just replacing f of x with y. Now what we do is we just solve for y. And so we're going to use the inverse functions. The first function, inverse of adding 5, we would subtract 5 to move it to the other side. So now we have x minus 5. So you can see instead of plus 5, the inverse function has a minus 5, equals 2y. Then we will do, instead of multiplying by 2, we're going to use the inverse function, which is divide by 2 and divide by 2. Oops, canceled out the y instead. And so here we have step 4. We've solved for y, so that's y equals x minus 5 over 2. And then all we have to do then is put it back in, I think that was step 3. Step 4 is to put it back in its original, it's a function notation. And so step 4 is to replace y with f inverse of x, because we used all the inverse functions to isolate the y. So now we have the inverse function here, f of x is equal to x minus 5 over 2. And I'm going to squeeze this in a little bit so we can see a little better. All right. Okay. And so in a minute I will show you how to check that. But for now, we have that done. Okay. All right. Next one. Here we have a quadratic function. So I'm actually going to draw that. That has a y-intercept of 2. And then it's opening up because our a term is, and it's opening up. So it looks something like that. Okay. And so we have constrained the function because this is not one-to-one. But if we constrain it to just x is greater than or equal to 0, then that means that we can get rid of this side of the function so that now it is one-to-one. And since now it is one-to-one with that constraint on the domain, I can find its inverse. So I'm going to switch this out with y equals 3x squared plus 2 over our restricted domain. By the way, it also has a range. If you notice, it has a range of 2 to infinity. That's important, and it has a domain of 0 to infinity. All right, now we're going to switch the x and the y. So we're going to do x equals 3y squared plus 2. And then we're going to start using our inverse operations to solve for y. So subtract 2. So x minus 2 equals 3y squared. Divide by 3. And if you don't mind, I'm going to go ahead and rewrite this as y squared equals x minus 2 over 3. And now to isolate, what's important here now is these y squared, for a function to be one-to-one and have an inverse, you have to be able to solve it for y equals, and this says y squared equals. So when we're going to have to take the square root of y squared and the plus and minus square root of x minus 2 over 3. But we are going to ignore the negative square root because we're looking for, our domain was restricted to all our x's were greater than or equal to 0, so we want the positive square root and not the negative square root. And so now we can go ahead and cancel that and put this back in function notation, writing it in inverse function of x is equal to the square root of x minus 2 over 3. And then just to double check of the domain of that, because it is under a square root, so we'd have to say x minus 2 over 3 is greater than or equal to 0. We'll multiply both sides times 3. So x minus 2 has to be greater than or equal to 0. So x has to be greater than or equal to 2. And so you can see that this has a domain of 2 to infinity. And if you recall, our range of our original function was also 2 to infinity. So that's a pretty good deal. And if we were to plug in a 2 under our square root, just as a check here, 2 minus 2 for our x, because that's our very first x, over 3, we get the square root of 0 over 3, or the square root of 0, which is 0. So that means that our range would start at, that'd be, it's very, that, because that's 0 is the very smallest number we can put in the square root. Our range would be 0 to infinity. And so there you go. That would be our inverse function there. So I'm going to go back and highlight here and here. I've got a bunch of mess here that I've got to get out of the way. So I'm going to move that out of the way. Move this out of the way. I think I should have made this note page. Before I give you guys a note page, I'm going to give you more room to do that math. All right, let's take a look at this last one here. So this last one is a rational function. Let's go ahead and see if we can't solve it. So this is going to be switching the g of x out for y. And then we're going to switch the x and the y. So that'll be x equals 1 over 3y squared, y minus 2. And then we're going to solve for y. But the problem is y is in the denominator. So, you know, we're going to have to clear the fraction. So we're going to multiply both sides times 3 minus 2 times 3y minus 2 so that we can cancel. And so here's what we have here. 3y minus 2 times x equals 1. I'm not going to distribute this x. That would be a really bad idea, because what I'm trying to do is isolate y, and the x is already pretty isolated from it. So what I'm going to do is just move it to the other side by dividing it instead of multiplying it. Use that inverse function. Okay, so we have that. So 3y minus 2 is equal to 1 over x. And then we'll use the inverse function to move the 2. So we're going to add 2 to the other side. So we have 3y equals 1 over x plus 2. Now the last thing we have to do is multiply, divide by 3, but I'd rather not divide by 3, and that's because I don't want to create that situation where I have a complex fraction. So I'm going to multiply by the inverse, or the reciprocal, which is also an option here. The reciprocal of 3 is 1/3, and if I multiply 1/3 times 3, it's just 1. So I'm going to go ahead and just multiply both sides times 1/3, just thinking ahead there. That's y equals, and we'll distribute. That's 1 over 3x plus 2 over 3. And I probably should clean that up a little bit so that we have common denominators. So I'm going to do that by giving both denominators, they're going to both want the x. Denominators are very jealous, so whatever this denominator had, this one wanted. Okay, so here's what we have. Y equals 1 plus 2x all over 3x, and that's probably the best form of that. Then putting that back in function notation. Now we used all the inverse functions, so this is the f inverse of x is equal to 1 plus 2x over 3x. So that one was fun. That one was a beast. Now how do we know that any of these we actually did find the right inverse function? So let's take a look at the theorem for inverse functions that says this. If I compose the f inverse of x into the original f of x and I simplify it, it should equal x for every x in the domain of the original function. And then what you have to do is not just check the inverse function composed inside the original function, you also have to go the other way and put the original function composed in the inverse function and see if that also simplifies to x. And this would be for every x in the domain of your inverse function. So those are your inverse theorems, and what you have to do is just use your algebra very carefully. So what we're going to do here is check your solutions for problem 2, set 2, using the inverse theorem here. So in example A, we had f of x was equal to 2x plus 5. And I'm just going to color code the f inverse of x, so its inverse function was x minus 5 over 2. Notice instead of plus 5 it was minus 5, and instead of times 2 it was divided by 2. Interesting how you can just look at it and see that they're actually inverse functions. Okay, so the first thing we're going to do is we're going to go ahead and take the original function, take out the x, and insert the composed, or the inverse function here, x minus 5 over 2. So all I'm doing is composing or inserting the f inverse of x in for x in the original function. Now let's simplify that. So I'm going to grab my back pen here. So first what I would do is I would want to multiply, because multiplication comes before addition, but I can cross simplify those 2's. So that leaves me with x minus 5 plus 5 equals x, and then you can see that that's x equals x. And so I'm halfway sure that that x minus 5 over 2 is actually the inverse function, but before we finish, we do have to go the other way and plug the original function into the inverse function. So the inverse function was x minus 5 over 2, so I'm going to leave the x out, minus 5 over 2, and I'm going to insert the original function, which was 2x plus 5. Just plugging that in for the x right here in this function. And then we'll go ahead, and that's supposed to equal x. All right, and so let's simplify that. So that would be 2x plus 5 minus 5. Oh, well, we could go ahead and cancel that out, and that would be 2x over 2, and then that would cancel that out, and that would be, that should not say equals 2, that should say equal x. Oh my goodness, I'm so scattered. I apologize. I'm going to do that again because that was a very bad example. All right, so I inserted, so we took out, I gotta get my regular eraser back here. Okay, so we took out the x from x minus 5 over 2 excuse me, and inserted 2x plus 5 in the place of x. Okay, so we have on the top of that fraction, we have addition and subtraction. And so that's a grouping symbol, the top of a fraction over the bottom of the fraction. So we could go ahead and cancel that out, and that would leave us with 2x over 2 equals x. And then, of course, we can cancel the 2 divided by 2, and so x equals x. And so we can verify for sure that these two functions are inverses of each other by composing them within each other and completely having their operations, their inverse operations, cancel each other out, just leaving us with an x. That's what's supposed to happen. This next one's a little more complicated than the last one's really more complicated. So with example B, we had f of x is equal to 3x squared plus 2. For x is greater than or equal to 0. And then our f inverse of x was the square root of x minus 2 all over 3, and that was for x is greater than or equal to 2. So we're going to be plugging those into each other. So we'll start by plugging the inverse into the original. So original was 3x squared plus 2, so we're going to remove the x and insert the inverse of x, and then we're going to go ahead and simplify that. And so first, order of operations, just recall please the inverse. The order of operations says first we do everything in parentheses, and then we do powers, and then we do multiplication and division, and then we do addition and subtraction. So when I'm looking at this problem here, right here, we have multiplication and we have a power, right? So we have to do the power first. So let's see. The power cancels the square root because roots, square roots, and squares are inverse operations, and so that would leave us with 3 times, I mean to do this in black pen to show that this is the next step. So 3 times x minus 2 over 3, the square root is gone, plus 2 equals x, and now we can multiply. Actually, because that's 3 over 1, we can go ahead and cross simplify, so the 3's are gone. So that's x minus 2 plus 2 equals x, and there we have x equals x. And that worked out quite well. All right, and so now we're going to go the other way by taking our inverse function, which is the square root of x minus 2, removing the x, and then equals x, and inserting the 3x squared plus 2. I had to squeeze that in there. That looks terrible. I think you guys have it though. Okay, so we've got a grouping symbol here. We've got 2 grouping symbols. We've got the square root, we've got the fraction. So we got to work within the grouping symbols first. So I think you can see that these two The 2 minus 2 cancels each other out, leaving us with 3x squared over 3 equals x. And then we still have this grouping symbol inside. We can actually simplify this fraction by canceling out the 3's, and so that leaves us the square root of x squared equals x, and squares and square roots cancel it out, and so x equals x, and there you go. So those are definitely inverse functions because they're using inverse operations to undo each other, so that all you're left with is an x. Let's go with the last one. This one will take a little bit more time. So it was a g of x. Actually, this should say g of x. So we're going to go with just fixing that up, okay? Just because we should have put that as a g of x as well, because it's a g of x. So the g of x was 1 over 3x minus 2. G of x, 1 over 3x minus 2. And then our f of x, or our g inverse of x, is 1 plus 2x over 3x. Ugh. Okay, so we'll start with our blue function here, our g function, and we're going to write 1 over, we're going to take the x out, so I'm going to use some parentheses here, minus 2, and we are going to insert 1 plus 2x over 3x. Okay, so the problem here, well, something we could do first to simplify this a little bit is cancel these 3's. So, oh, that's supposed to equal x. So 1 over 1 plus 2x over x minus 2 equals x. Now, this is a complex fraction, so the best thing we can do is just multiply everything in the fraction by x to clear the fraction. So let's do that. Let's do that. Let's go. Okay, so we're going to multiply this times x, we're going to multiply this times x, so we're going to multiply that times x so that we can go like this, and that looks a bit better. That'll cancel some things out. So here we have x over 1 plus 2x minus 2x equals x. And then we can simplify now what's on the bottom. Those two x's cancel out, leaving us with x over 1 equals x. And so finished up, x equals x. And so just a really nice way here in this step is because you have that extra x in the denominator there. If you multiply everything in that fraction times x, you can cancel it out. It becomes a simple fraction, and then it's easier to simplify. Okay, then this other one here, we're going to do the g inverse of g of x. So let's write the g inverse out. 1 plus 2, take out the x, over 3, take out the x. So we're going to plug in our g of x function, which is 1 over 3x minus 2 and 1 over 3x minus 2. And this is supposed to equal x. Okay, so let's go about simplifying that. So I think the best thing we could do, again, because we have this denominator here and here, they're both 3x plus minus 2 if we were to multiply everything by that. So I'm just going to do a different step here. I'm going to do 3x minus 2. Actually, I'm going to copy paste this. So that you can see this next step. All right, so what I'm going to do is I'm going to go ahead and I'm going to distribute that 3. I'll go ahead and distribute that 3. So, okay, I'm sorry. I'm going to do this one more time. Let me distribute the 3 and then simplify. So we have 1 plus 2. I'm going to go ahead and distribute that 2. 2 over 3x minus 2 over, and distribute this 3 here. 3 over 3x minus 2 equals x. And now I'm going to clear the 3x minus 2 from the two complex parts of that fraction by multiplying everything by 3x minus 2, by 3x minus 2, and by 3x minus 2, so that I can cancel all of that. And then here we'll simplify. So 3x minus 2 times 1 is just 3x minus 2 plus 2 all over 3 equals x. So you can see that's working out quite nicely. And then we'll cancel, the 2's will cancel. So we have 3x over 3 equals x, and cancel through division, x equals x. Okay, so there's the algebraic way to prove that two functions are inverses of each other by composing them within each other and using their inverse operations to completely remove all values except for x. And that's how it is. And so good luck with tonight's homework. You have, I think, 8 or 9 problems to do. And I will see you tomorrow. Bye.